This work was part of a larger project to assess the usability of GPS traces, volunteer geographic information system within spatial interaction modeling. So I was tasked with writing some code to carry out the spatial interaction modeling. So before I get into that, I'll overview spatial interaction, what I mean by that, and the models that I'm talking about. I'll talk about gravity models and then the maximum entropy framework. I'll distinguish between model calibration and flow prediction, so two main uses of these models. And I'll talk about the most common methods for calibrating the models, regression and maximum likelihood estimation. And then I'll talk about the code that I wrote, pySI for pySpatial interaction. I'll talk about the goals, the input data format. I'll do some examples on calibrating models and how I validated the routines, and then I'll show how you can use the software as well to estimate flows and talk about some future additions. So spatial interaction is broadly defined as the flow or movement from an origin to a destination. Those flows can be people, commodities, information. And spatial interaction system consists of more than one origin or destination in which the general relationship is, say, in terms of people, the larger populations between two cities would draw larger flows, whereas the flows will decrease over longer distances. And normally those flows are encoded in a matrix where the rows represent origins and the columns destinations. And the column totals will give you the total flows into a destination, whereas the row totals will give you the total flows originating at each origin. And this was encoded mathematically with an analogy to Newton's law for gravity, so it's termed a gravity model. Ti of j represents the estimated flows, whereas Vi and Wj are either variables or a vector of variables, which would represent your origin and destination attributes. So say the population at an origin or destination. Di of j is the distance between those that origin and destination, and the term k is a scaling factor to ensure the magnitude of flows matches the inputs. Later, freely varying exponential parameters were added to each model term to capture the individual relationships between model terms and the flows. However, it was simply a physical analogy, and one framework to improve upon that was the maximum entropy framework, which sought to find the most probable distribution of flows given no additional information in the system. So for a simple example here, if you have one origin and two destinations and you have 30 flows that you want to allocate, you'd seek to find the two aggregate flows to the destinations, which can be fulfilled by the highest number of unique individual flow combinations. So the most number of unique flow combinations in this example would be given by 15 flows to each destination. And the number of unique combinations can be described by the equation R. By maximizing R, you are essentially finding which one would be the most probable. Oops. By maximizing, I have H there, sorry. Maximizing R with regards to various constraints results in different models. It's maximizing with various constraints as well as a whole bunch of algebra. But you get a family of what's dubbed a family of spatial interaction models. And the unconstrained model is the same as the gravity model I presented earlier, but the K factor drops out because there is the single constraint that the total number of flows within the system is conserved, so you don't have to worry about the units. The production constrained model adds in the term OI, which is that sum of flows originating at each location, and adds in a balancing factor AI, which conserves the number of flows starting at each location. So in a production constrained model, we seek to ensure that the number of flows in our observed data starting at each location is also the same in the estimated data that we produce. And this is very useful for looking at how, say in the terms of people, how they would choose to move to an origin, so you can investigate the factors which make a destination more attractive. The attraction constraint model is a mirror image of that. So we then introduce information about the total number of flows finishing at a destination, and this is useful for seeing why people might want to leave an origin. The doubly constrained model introduces both of those, the OI and DJ terms, as well as both balancing factors, and this is usually gives you the most predictive power in a model since you're introducing the most amount of information. In all of these models, the distance term often takes the form of an exponential or power function. So right now, di of j is just wrapped in a generic function, but that's usually exponential or power. And I'll just differentiate between calibration and prediction. Calibration is deriving the relationships between the flows and each variable using the observed data. So for example, we would have all of the model terms except for those exponential parameters, and that's what we would seek to find in calibration. Whereas in prediction, we have all of the model terms and we have those parameters, but we would like to predict flows or simulate flows. One method for calibrating the models is a regression framework. And first, you have to make the equation linear. And so you can do that by taking the log of all of the model terms. And this is pretty simple to do in an R or stats model framework. You would get an input string, something like that. But the one large problem with calibrating in regression is zero flows and taking the logarithm of 0, which is not possible. So it's pretty limited in that you have to have a system where there are a positive number of flows from every single origin to every destination, which is not necessarily realistic in many systems. So you can solve that by using maximum likelihood estimation routine. And this seeks to find parameter estimates that maximize the likelihood of observing a sample set of interactions from a theoretical distribution. And that process looks a bit like these 3 steps where you'd need to identify the theoretical distribution that you want your data to match. It would maximize the log likelihood function of that distribution with respect to each parameter you're including in the model. And then you want to derive equations which ensure the maximization of those log likelihood functions. And so I'm not going to go over that process, but in terms of in this application, that process would yield the following equation for every parameter in the model that you are looking to calibrate. So you get a series of equations which you want to solve. I'm not going to go over this flow chart, but this would be the sort of algorithmic flow to calibrate a doubly constrained model. And I just wanted to note that for each of the changing model terms or balancing factors and varying inputs to different applications, that algorithmic flow can change. And so it can be quite complex depending on which model you want to run. And in terms of existing calibration tools, like I said, you could calibrate in R, and there's a paper from UCL which outlines how to do the doubly constrained model in an R framework. And there was some code in Fortran for doing maximum likelihood estimation for spatial interaction models, but I think it's no longer accessible. So there's very few solutions that are existing, and I thought that leveraging Python would be a great way. You could write scripts and some functions to access them. And so my goals for spatial interaction were to have core functionality, so a place where you could run all 4 of those different models, but also using either regression or maximum likelihood estimation, and you could compare the results amongst them. Something that was fast enough to run, at least on just a regular notebook. Simple enough that you didn't have to know the math or statistics to run these models. And flexible in that you could quickly change between them or run them multiple times. So I built it on top of Pandas. The input data uses a Pandas data frame. Use SciPy to optimize to carry out the optimization of the log likelihood functions, stats models for the regression, and some NumPy for basic math on arrays. I ended up with 2 classes, which I called pySI.calibrate and pySI.simulate to differentiate between calibrating a model versus predicting flows. And just real quick, the input data format is this data frame. So data represents observed flows between origins and destinations. di of j is the distance between that origin and destination. The origin and destinations are just telling you where flows start and end. And the population is the population at destinations in this case. So first example of a calibration is 1970 airline passengers from Atlanta to 24 other major cities in the US. And I've chosen this data because it was published along with the original Fortran code, so I could compare my results to theirs. And the first line is just reading in the data. And then the next few lines are the parameter inputs. So you have you have to specify where your origins are, your destinations, what your observed flow data is, your distances. We have to specify the function for your distance parameter, which I said was either power or exponential. So those are the two that are currently included. In this case, power function. The factors which you want to describe your origins or destinations. And so in this case, it's a production constrained model. So we're including all the information about how many flows start at the origin. So we don't need a factor to describe that. But we have to tell that we want population to describe how attractive each destination is. And then lastly, you would have to include the constraint information. So in this case, I'm using a dictionary where the keys are either production or attraction, and then you would tell it which field represents what you're constraining on. So in this case, it's origin constrained, production constrained model, and the origin column is representing my origins. And then I instantiate a pySI calibrate object. And saving it in the model variable there, and that takes all of those inputs. And then I'm calling the maximum likelihood function on that model. In this case, for maximum likelihood estimation, you have to include initial parameters, initial parameter estimates, and those are pretty much always the same. For a beta or a distance parameter, it's always 0, and for your factors, it's always suggested to start with 1. But you're free to change that if you wish. And running that model, I've compared the Fortran, what's called SimMod. I'm comparing some statistics from the Fortran code with my code. And I've got the parameter estimates along with their standard errors and an R² for the model. And so for all of those statistics, I get pretty much the same values. It's not the greatest model, but just a quick scatter plot to show the correlation of the model with the observed flows with how well it then estimates flows. And the second example is 2006 migration in Austria. And this is the data that was used in the paper describing how to calibrate a model using regression. So comparing here the maximum likelihood estimation routine with regression. And in the case of a doubly constrained model, they should be equivalent. In this case, I've changed the distance function to exponential. I have removed the factors because in doubly constrained model we don't need additional factors to describe the system. And I've added in the additional constraint that it's now a production and attraction constrained model. And I've just modified the initial initial parameter values. In this case, I get the exact same beta parameter, I get the same error on the beta parameter, and the same R² for the model. And it's an R² of about 0.98, which is a pretty strong model. So just the distance alone within that model is able to predict pretty well the flows. And the last example I looked at was 2001 London work commutes. In this case, it's a production-constrained origin-specific model. So we've run the model from one origin to all other destinations. We're seeking to allocate flows, but we do that for every single origin. In this case, it's the 33 boroughs of London. And so I just use a simple loop to run through and run that model 33 times. It's a bit harder to compare statistics in this case because you get 33 sets, 33 beta parameters. And so for this, I've used a choropleth map just to validate that. And it's pretty strong correlation. So the boroughs that are farther from London, people seem to be, the darker blue represents a more negative parameter, which means people are less likely to travel over long distances. So that sort of makes sense. People probably aren't commuting as much. If you're closer to London, you're probably more likely to commute into London. And the city of London itself in the center has a pretty strong negative parameter because people from London probably have no reason to commute very far at all. So they're all staying where they are. And then I have one example of forecasting with a calibrated model. So if you want to calibrate a model and perhaps change something in your system, say remove a node or simulate what would happen if you doubled the population at a specific origin or destination, you can instantiate a simulate object and you can pass in the results from the calibrate object and then use the entropy function to recalculate the entropy model using a few different inputs here. So here I have a remove node input, set params in case you'd like to see what happens, say, if you increase or decrease the exponent related to a parameter, or if you'd like to change the factors such as population associated with a node. And so just finishing up, I'm working on adding in competing destinations, which is part of an extension to the Max-Entropy framework, which seeks to add in a model that's based on spatial behavior and discrete choice modeling. I'm also looking to add in the radiation model, which is separate from the Max-Entropy framework. This way you can compare, you could easily run two models in different frameworks and compare them. Some alternative calibrations. One example is particle swarm optimization, which is a heuristic technique rather than statistical. And the one visualization I showed is not currently done in Python, so I'd hope to just add in some plotting features so you can validate your results. And then to benchmark the scaling capabilities. So the examples I showed take anywhere from a half a second to about 15 seconds to calibrate. And I've run one model which used about 550 origins and destinations, and that took about 10 minutes to calibrate. So if you wanted to do an origin-specific model and run it 550 times, that's probably too slow for that. So see exactly how it scales up and then see if I could do anything to speed that up. So just to conclude, just went over a review of spatial interaction. And then in terms of pySI, so far it's fast enough to run in a notebook, but if you want to do larger models, I'm not sure that's going to remain, so it might need to be optimized a bit. It's simple in that you don't need to use, you don't need to have any intimate knowledge of the math and statistics behind it, but it does take a few lines of code, and flexible that you can run between the different models pretty quickly by changing the inputs. And so I hope it can act as a core functionality to build upon. And add in other models. This way you can do side-by-side comparisons to better understand how different models can give you different results. So just thanks to CGI and GeoCrowd for providing the resources to come out, and thanks for listening.
Thank you, Taylor.